Welcome everyone to this presentation on optimization methods. Today, we'll embark on a journey to understand the fundamentals of optimization and how it plays a pivotal role in solving complex problems across various fields. Here's an overview of what we'll cover in this section. We'll start with the definition of optimization, discuss its importance in different domains, explore some common optimization techniques, and finally, introduce particle swarm optimization as a powerful method for solving complex problems. First, let's define optimization. In simple terms, optimization is the process of finding the best possible solution from all available options. It's about making things as effective or functional as possible by selecting the optimal choice among many feasible alternatives. Mathematically, optimization involves maximizing or minimizing an objective function. This is achieved by systematically choosing input values within an allowed set and calculating the corresponding output of the function to find the optimal result. The objective function, often denoted as f of x, represents the goal of our optimization problem. It could be anything from minimizing costs, maximizing efficiency, to achieving the best performance metrics in a system. Constraints are the limitations or conditions that our solutions must satisfy. The feasible set is the collection of all possible solutions that meet these constraints. Optimization seeks the best solution within this feasible set. This graph illustrates an objective function with a clear minimum point. Our goal in optimization is to find this point where the function attains its optimal value. Optimization is crucial because it helps us enhance performance, reduce costs, and improve efficiency in various systems and processes. By finding the optimal solution, we can make the most effective use of resources. In engineering, optimization plays a key role in design processes. Engineers use optimization to create structures that are strong yet lightweight, design mechanical systems that operate efficiently, and develop electrical circuits that perform effectively while minimizing energy consumption. In economics, optimization helps in resource allocation by determining the most efficient way to distribute limited resources. Businesses use optimization to maximize profits, minimize operational costs, and develop optimal investment strategies. In machine learning, optimization is fundamental for training models. Algorithms adjust parameters like weights and biases to minimize loss functions, which leads to models that make more accurate predictions. Optimization is also vital in logistics for efficient route planning and supply chain management, and in healthcare for optimizing treatment plans and scheduling resources effectively. Several traditional optimization techniques have been developed over the years, each with its own strengths and areas of application. Let's take a brief look at some of these methods. Gradient descent is an algorithm that finds the minimum of a function by moving in the direction opposite to the gradient. At each step, it calculates the derivative of the function with respect to its parameters and updates the parameters accordingly to minimize the objective function. However, gradient descent has some limitations. It requires the objective function to be differentiable, may get stuck in local minima in non-convex functions, and its performance is sensitive to the choice of learning rate. Genetic algorithms simulate the process of natural evolution. They work with a population of candidate solutions, applying operations like selection, crossover, and mutation to evolve solutions over generations, aiming to find the best or near-best solution. Genetic algorithms are used in various applications, including scheduling problems where tasks need to be assigned efficiently, design optimization in engineering, and feature selection in machine learning to improve model performance. Simulated annealing is inspired by the annealing process in metallurgy. It allows the algorithm to occasionally accept worse solutions, enabling it to escape local minima and explore the solution space more broadly. Over time, the algorithm reduces the probability of accepting worse solutions, cooling down to focus on refining the best solutions found. Despite their usefulness, traditional optimization techniques can have drawbacks, such as high computational costs, especially for complex or high-dimensional problems. They may also require the problem to be formulated in a specific way, limiting their applicability. As optimization problems become more complex, involving nonlinear, non-differentiable, or high-dimensional functions, there's a need for advanced algorithms that can handle these challenges effectively and efficiently. This brings us to swarm intelligence, which studies the collective behavior of decentralized, self-organized systems in nature. Examples include bird flocking, where birds coordinate their movements, fish schooling for protection, and ant colonies finding the shortest paths to food sources. Swarm intelligence is based on simple agents following basic rules and interacting locally with one another. These interactions lead to complex, emergent global behavior without centralized control, making it an attractive model for solving complex problems. Applying swarm intelligence to optimization offers several benefits. The system is robust to the failure of individual agents, can be parallelized and scaled easily, and adapts well to changes in dynamic environments. Particle swarm optimization, or PSO, is an algorithm inspired by the social behavior patterns of organisms like birds and fish. It has proven effective in handling complex optimization tasks across various domains. PSO is favored because of its simplicity and ease of implementation. It requires few parameters to adjust and doesn't need gradient information, making it suitable for optimizing nonlinear and non-differentiable functions. In the upcoming sections, we'll dive deeper into how PSO works, explore its mathematical foundations, and look at practical applications and examples to illustrate its effectiveness. To wrap up this introduction, we've learned that optimization is essential in numerous fields. Traditional methods can have limitations. Swarm intelligence provides a promising alternative, and particle swarm optimization is a powerful tool that leverages these concepts. Now, let's delve into particle swarm optimization, commonly known as PSO. This innovative algorithm has revolutionized how we approach complex optimization problems by drawing inspiration from nature. PSO was developed in 1995 by James Kennedy, a social psychologist, and Russell Eberhardt, an electrical engineer. Their collaboration bridged social sciences and engineering, leading to the creation of this powerful optimization technique. The key inspiration behind PSO comes from observing social behaviors in nature, such as bird flocking and fish schooling. These phenomena showcase how simple individual behaviors can lead to complex group dynamics without centralized control. Swarm intelligence refers to the collective behavior of decentralized systems. It's about how individual agents interact locally with one another and with their environment, leading to the emergence of intelligent global behavior. In PSO, we consider a group of particles, each representing a potential solution to our optimization problem. These particles move through the search space, exploring different solutions to find the optimal one. Particles adjust their positions by learning from their own experience and the experience of neighboring particles. This means each particle is influenced by both its personal best position and the best position found by the swarm. Every particle keeps track of its personal best position, known as P-best, which is the best solution it has achieved so far. The global best, or G-best, is the best solution found by any particle in the entire swarm. Particles update their velocities and positions by considering both their personal best and the global best. This approach balances the exploration of new areas in the search space with the exploitation of known good solutions. The velocity of each particle is updated using the following equation. Vi, t plus 1, is the new velocity of particle I. W is the inertia weight, controlling the impact of the previous velocity. C1 and C2 are acceleration coefficients for cognitive and social components, respectively. R1 and R2 are random numbers between 0 and 1. Xi, t, is the current position of particle I. P-best I is the personal best position of particle I. G-best is the global best position found by the swarm. After updating the velocity, each particle's position is updated using xi, t plus 1, equals xi, t, plus vi, t plus 1. This means the new position xi, t plus 1, is calculated by adding the new velocity vi, t plus 1, to the current position xi, t. Imagine particles moving through the search space, adjusting their paths based on their own success and that of their peers. Over time, they tend to converge towards the most promising areas, leading to an optimal or near-optimal solution. PSO stands out due to its simplicity and efficiency. It doesn't require gradient information, making it suitable for complex or non-differentiable functions. Additionally, it involves only a few parameters, easing the tuning process. Since PSO doesn't rely on gradient information, it's ideal for optimizing functions that are non-differentiable, discontinuous, or noisy. This expands its applicability to a wide range of real-world problems where traditional methods may falter. PSO is straightforward to implement, requiring basic mathematical operations. Its simplicity translates to lower computational costs, making it practical for problems where resources are limited. Only a handful of parameters influence PSO's performance. The inertia weight controls the impact of previous velocities, while the cognitive and social coefficients determine how much a particle is influenced by its own experience and that of the swarm. PSO's versatility has led to its adoption in various fields. Let's explore some of the key areas where PSO has made a significant impact. In neural networks, PSO is used to optimize weights and biases, effectively training the network. By finding the optimal parameters, PSO improves the network's learning efficiency and predictive accuracy. PSO assists in tuning parameters of control systems, such as PID controllers. By optimizing these parameters, PSO enhances system stability and response, leading to better overall performance. In scheduling, PSO helps allocate resources effectively, ensuring tasks are completed in an optimal order. This reduces delays and operational costs, improving efficiency in industries like manufacturing and logistics. PSO's flexibility extends to data clustering, where it groups similar data points without prior knowledge of groupings. It's also used in image and signal processing for feature extraction and in financial modeling for portfolio optimization. Real-world applications of PSO include optimizing energy management systems for better efficiency and designing aerospace components that meet strict performance criteria while minimizing weight. To summarize, particle swarm optimization is a nature-inspired algorithm that offers a simple yet powerful approach to solving complex optimization problems. Its wide applicability makes it a valuable tool across various disciplines. Let's explore the fascinating biological phenomena that inspired particle swarm optimization. Understanding these natural behaviors will provide deeper insights into how PSO works and why it's so effective in solving complex problems. In nature, many species exhibit social behaviors that enhance their survival. These behaviors often involve collective movement and decision-making, allowing groups to adapt to their environment more effectively than individuals could alone. Consider how birds flock together. Each bird adjusts its flight path based on the movements of its neighbors. This coordination conserves energy through aerodynamic advantages and improves navigation during long migrations. The mechanics involve three simple rules: alignment with nearby birds, cohesion towards the group center, and separation to prevent collisions. These simple interactions result in the complex, fluid motion of a flock. Flocking offers several advantages. Birds expend less energy by riding air currents created by others, there's safety in numbers against predators, and they can find food sources more efficiently through shared information. Similarly, fish exhibit schooling behavior. By moving cohesively, fish create complex patterns that can confuse predators and reduce individual risk, enhancing the survival of the group. Fish adjust their speed and direction based on their neighbors. This synchronization allows the school to react quickly to threats and opportunities, changing formations dynamically as needed. Both bird flocking and fish schooling demonstrate that simple local interactions can lead to sophisticated global behavior. Importantly, there's no leader dictating movements. Instead, the group's behavior emerges from individual actions following simple rules. PSO models these natural mechanisms by allowing particles to share information about good positions in the search space and adjusting their movements accordingly. This collective behavior enables the swarm to converge on optimal solutions. Each particle remembers its personal best position and is also aware of the global best position found by the swarm. This dual awareness allows particles to benefit from both individual and collective experiences. Particles adjust their velocities based on their own success and the success of the group. This results in a balance between exploring new areas, diversification, and exploiting known good areas, intensification. By mimicking these efficient natural processes, PSO benefits from the inherent robustness and adaptability observed in biological systems. This leads to an algorithm that's capable of handling complex, dynamic optimization problems effectively. By mimicking these efficient natural processes, PSO benefits from the inherent robustness and adaptability observed in biological systems. This leads to an algorithm that's capable of handling complex, dynamic optimization problems effectively. Just as natural swarms can adapt to changes in their environment, PSO is robust against changes in the optimization landscape. The stochastic elements help the swarm escape local optima, enhancing the algorithm's overall effectiveness. Biomimetic algorithms like PSO are particularly effective for dynamic optimization problems, where the optimal solution changes over time, and for complex functions with many local optima. They also perform well in real-world environments that are noisy or unpredictable. In summary, the social behaviors observed in nature provide a blueprint for creating efficient optimization algorithms. PSO models these behaviors, resulting in a powerful tool capable of solving a wide range of complex problems. In next section, we'll explore the fundamental mechanics of particle swarm optimization, or PSO. Understanding these basics will provide insight into how PSO operates and why it's effective in solving complex optimization problems. In PSO, each particle in the swarm represents a potential solution to the optimization problem. Think of particles as agents that navigate the solution space, each characterized by a position and a velocity. The position of a particle, denoted as x sub I, is a vector comprising its coordinates in the solution space. For example, x sub I equals x sub I1, x sub I2, and so on up to x sub In, representing its location in n-dimensional space. Each particle also has a velocity vector, v sub I, which dictates how it moves through the solution space. The velocity components influence both the direction and speed, guiding the particle toward promising areas. Particles navigate the solution space by continuously updating their positions and velocities. Through this iterative process, they explore different regions in search of the optimal solution. The velocity of each particle is updated using the following equation. V sub I at time t plus 1 equals W times V sub I at time t, plus C1 times R1 times open parenthesis best sub I minus X sub I at time t close parenthesis, plus C2 times R2 times open parenthesis G best minus X sub I at time t close parenthesis. Let's break down what each term represents. The velocity update consists of three key components. The inertia term, W times V sub I at time t, encourages the particle to continue moving in its current direction. The cognitive term, C1 times R1 times the difference between best sub I and X sub I at time t, draws the particle toward its personal best position. The social term, C2 times R2 times the difference between G best and X sub I at time t, pulls the particle toward the global best position found by the swarm. After updating the velocity, the particle's new position is calculated using x sub I at time t plus 1 equals x sub I at time t plus v sub I at time t plus 1. This means the new position is the sum of the current position and the updated velocity. Each particle keeps track of its personal best position, known as best. If a particle discovers a position that yields a better objective function value than its previous best, it updates best to this new position. The global best position, or G-best, is the best solution found by any particle in the swarm. It serves as a benchmark that guides all particles toward the most promising area in the search space. At each iteration, particles evaluate their current position. If a particle's current fitness is better than its best fitness, it updates best. Similarly, if any particle's best is better than the current gbest, the swarm updates gbest. PSO balances two critical aspects. Exploration involves particles searching new areas in the solution space to discover potential solutions. Exploitation focuses on refining existing solutions by honing in on known good positions. This balance prevents the swarm from getting trapped in local optima and promotes finding the global. The inertia weight, denoted as W, affects the particle's momentum. A higher inertia weight encourages particles to explore the search space broadly, while a lower inertia weight focuses the search around the current best positions. The coefficients C1 and C2 determine the relative influence of personal and social components on the particle's velocity. C1, the cognitive coefficient, reflects how much the particle relies on its own experience. C2, the social coefficient, represents the influence of the swarm's collective experience. The random variables R1 and R2 are uniformly distributed between 0 and 1. They introduce randomness into the velocity update, promoting diversity in the swarm's search patterns and helping prevent premature convergence. Imagine particles scattered across the solution space. As iterations progress, they adjust their velocities and positions, gradually converging toward the optimal solution by following both their own best positions and the swarm's best. Let's consider a simple example where we calculate a particle's new velocity and position based on its best and the gbest. This will illustrate how the particle moves closer to optimal solutions over time. Selecting appropriate values for the inertia weight and the cognitive and social coefficients is essential. The right balance ensures that the swarm converges efficiently without missing the global optimum. In summary, PSO operates by having particles, which represent potential solutions, move through the solution space. Their movements are influenced by both their personal best experiences and the swarm's collective best. This balance allows the algorithm to efficiently search for the optimal solution. Next, we'll delve deeper into the mathematical foundations of PSO, exploring the key equations in more detail and discussing how to select and tune parameters for optimal performance. In this section, we'll delve into the mathematical equations that form the backbone of particle swarm optimization. Understanding these equations will give us deeper insights into how PSO functions and how we can fine-tune it for optimal performance. The core of PSO lies in the velocity update equation. V sub I at time t plus 1 equals W times V sub I at time t, plus C1 times R1 times open parenthesis best sub I minus X sub I at time t close parenthesis, plus C2 times R2 times open parenthesis gbest minus X sub I at time t close parenthesis. Let's break down the components. W, the inertia weight, controls how much the particle's previous velocity influences its current velocity. C1, the cognitive coefficient, determines how much the particle is influenced by its own best position. C2, the social coefficient, dictates how much the particle is influenced by the swarm's best position. R1 and R2 are random numbers between 0 and 1 that introduce stochasticity, helping the swarm explore new areas. The inertia weight W plays a crucial role in balancing exploration and exploitation. A higher W value encourages particles to explore the search space more broadly, while a lower W value focuses the search around known good positions. The cognitive coefficient C1 influences how much a particle trusts its own past experiences. It pulls the particle toward its personal best position, encouraging individual exploration. The social coefficient C2 represents the particle's tendency to follow the success of the swarm. It pulls the particle toward the global best position found by any particle in the swarm, promoting collective convergence. The random numbers R1 and R2 introduce unpredictability into the particle's movements. This randomness helps the swarm to avoid getting trapped in local optima by encouraging particles to explore new directions. Once the new velocity is calculated, we update the particle's position using x sub I at time t plus 1 equals x sub I at time t plus v sub I at time t plus 1. This means the new position is simply the sum of the current position and the newly updated velocity. The inertia term, W times v underscore I, t, helps particles maintain their current motion. This momentum allows particles to explore the search space more effectively, potentially discovering new areas that lead to better solutions. The cognitive term, C1 times R1 times P best underscore I minus X underscore I, T, represents the particle's own experience. It draws the particle back toward the best position it has found so far, reinforcing successful behaviors. The social term, C2 times R2 times G best minus X underscore I, T, models the particle's inclination to follow the swarm's success. It pulls the particle toward the best solution found by any member of the swarm. Together, these three terms balance the exploration of new areas and the exploitation of known good solutions. The inertia term encourages particles to explore, while the cognitive and social terms focus the search on promising regions. This graph illustrates how particles adjust their velocities and positions over time. You can see particles moving through the search space, influenced by their p-best and the g-best, gradually converging toward the optimal solution. Here, we visualize the contributions of each velocity component over iterations. The inertia component decreases over time, while the cognitive and social components guide the particle toward better positions. Adjusting the parameters W, C1, and C2 affects how the swarm searches the solution space. For instance, a higher W promotes exploration but may slow convergence, while higher C1 or C2 values influence the particles to rely more on personal or social knowledge, respectively. Typically, W is set between 0.4 and 0.9, while C1 and C2 are often both set to 2.0. However, adaptive strategies that adjust these parameters during the run can enhance performance by balancing exploration and exploitation dynamically. To ensure the algorithm converges to a satisfactory solution, we can set criteria such as a maximum number of iterations, minimal improvement in g-best, or an acceptable error threshold. When particles move outside the feasible search space, we need to handle constraints appropriately. This can involve reflecting the particle back into the space or resetting its position to the boundary value. For effective implementation, it's advisable to initialize particles uniformly across the search space, use a decreasing inertia weight to shift from exploration to exploitation, and maintain diversity through randomization. In summary, the mathematical foundations of PSO are built on straightforward equations that model the particle's movements. The key parameters and terms work together to enable the swarm to find optimal solutions efficiently. Next, we'll explore the key parameters of PSO in more detail and discuss how they influence the algorithm's performance, enabling us to fine-tune PSO for specific optimization problems. In this section, we'll delve into the key parameters that significantly influence the performance of particle swarm optimization. Understanding these parameters is crucial for effectively tuning the algorithm to solve complex optimization problems. The swarm size refers to the number of particles used in the PSO algorithm. Typically, this ranges from 20 to 50 particles. Selecting an appropriate swarm size is important because it affects the algorithm's ability to explore the search space and the computational resources required. The inertia weight, denoted as W, controls the impact of a particle's previous velocity on its current one. A higher inertia weight encourages particles to explore the search space more broadly, promoting global exploration. Conversely, a lower inertia weight focuses the search around the current position, encouraging local exploitation. To balance exploration and exploitation, it's common practice to decrease the inertia weight over time. Starting with a higher value like 0.9 allows for broad exploration in the early stages. Gradually decreasing it to around 0.4 helps the particles fine-tune their search in promising regions as the algorithm progresses. The cognitive coefficient, C1, determines how much a particle is influenced by its personal best position. A higher C1 value means that particles will place more emphasis on their own experience, which can enhance individual exploration but may reduce the influence of the swarm's collective knowledge. The social coefficient, C2, controls how much a particle is influenced by the global best position found by the swarm. A higher C2 value encourages particles to align with the swarm's best solution, promoting convergence but potentially reducing diversity if set too high. Balancing C1 and C2 is critical. If C1 is much higher than C2, particles may overly focus on their own search, possibly neglecting beneficial information from the swarm. Conversely, if C2 is much higher, particles may converge prematurely, missing out on potentially better solutions. The random numbers R1 and R2 are uniformly distributed between 0 and 1. They introduce stochasticity into the velocity update, ensuring that particles don't move in a strictly deterministic way. This randomness helps maintain diversity in the swarm's search patterns. By introducing randomness, R1 and R2 help prevent the swarm from getting trapped in local optima. They encourage particles to explore new areas of the search space, increasing the likelihood of finding the global optimum. A widely adopted guideline is to set both C1 and C2 to 2.0. This gives equal weight to personal and social experiences. Starting with an inertia weight W of 0.9 and decreasing it to 0.4 over time balances the need for exploration and exploitation. Proper tuning of these parameters is essential because they directly impact the algorithm's convergence speed and the quality of the solutions found. Depending on the specific problem, you may need to adjust these values to achieve optimal performance. Adaptive strategies involve changing parameters like W, C1, and C2 dynamically as the algorithm runs. This can help maintain an effective balance between exploration and exploitation throughout the optimization process, potentially leading to better results. When implementing PSO, it's often effective to start with the standard parameter values and observe the algorithm's performance. If you notice issues like premature convergence or slow progress, consider adjusting the parameters to better suit your specific problem. Visual tools can help illustrate how different parameter settings affect the algorithm's convergence. By plotting the swarm's performance over time with various parameters, you can gain insights into the optimal settings for your problem. In summary, the key parameters of PSO, swarm size, inertia weight, cognitive and social coefficients, and random factors, are crucial for the algorithm's success. Understanding and properly tuning these parameters can significantly enhance PSO's performance on your optimization tasks. Next, we'll see how these parameters come into play by applying PSO to solve a specific optimization problem. We'll walk through the step-by-step configuration of the PSO algorithm tailored to our problem. In this section, we'll visually explore how particles in particle swarm optimization move and converge toward the optimal solution. Visualizations help us understand the dynamic behavior of particles during the optimization process. At the start of the PSO algorithm, particles are randomly distributed throughout the search space. This randomness ensures a wide coverage, increasing the chances of finding the global optimum. Here's a 2D plot displaying the positions of particles after the first iteration. Each dot represents a particle's current position in the search space. As the algorithm progresses, particles adjust their positions based on their personal best and the global best positions. These plots at iterations 5, 10, and 20 show how particles are moving through the search space. This plot illustrates the trajectories of particles over multiple iterations. The lines trace the paths particles have taken, highlighting how they explore and exploit different areas. Over time, you'll notice particles starting to cluster around certain regions. This clustering indicates that particles are honing in on areas with better objective function values. Eventually, the swarm converges toward the global optimum. Most particles are located near the best solution, demonstrating the algorithm's effectiveness in finding optimal results. An animation of particle movement vividly demonstrates how particles navigate the search space. Watching particles move can provide deeper insights into the dynamic behavior of PSO. Initially, particles are widely spread out, exploring various regions. As they update their velocities and positions, influenced by their personal best and the global best, they gradually cluster toward optimal solutions. In the early stages, the swarm focuses on exploration, searching broadly across the search space. In later iterations, exploitation becomes more prominent as particles fine-tune their positions around the best solutions found. The way particles move and converge is influenced by PSO parameters like inertia weight and cognitive and social coefficients. Adjusting these parameters can alter the balance between exploration and exploitation, affecting how quickly and accurately the swarm converges. This graph shows how the best fitness value improves over iterations. It illustrates the swarm's progress in finding better solutions as the algorithm runs. Visualizing particle movement helps us grasp the underlying dynamics of PSO. Observing how particles explore and exploit the search space enhances our understanding, enabling us to optimize the algorithm's performance for specific problems. Now that we've visualized how particles move and converge in PSO, we'll proceed to discuss the advantages of using this algorithm and how it compares to other optimization methods. In this section, we'll explore the key advantages of particle swarm optimization and understand why it has become a popular choice for solving complex optimization problems. One of the most significant advantages of PSO is its simplicity. Let's delve into what makes PSO straightforward and easy to use. PSO is easy to implement because it relies on simple mathematical operations like addition, subtraction, and multiplication. This means you don't need advanced mathematical knowledge to code and execute the algorithm. Unlike other optimization algorithms that use complex operators like crossover and mutation, PSO doesn't require these. This simplicity reduces the potential for implementation errors and makes the algorithm more accessible. Another advantage is that PSO has relatively few parameters to adjust, making the tuning process less complex compared to other algorithms. The primary parameters in PSO are the inertia weight, denoted as W, and the cognitive and social coefficients, C1 and C2. Managing just these key parameters simplifies the optimization process. With fewer parameters, you spend less time tweaking and more time solving the actual problem. This efficiency is a significant benefit when working with tight deadlines or limited resources. PSO's versatility is another major advantage. Let's see how it applies to a wide range of optimization problems. PSO can handle both linear and nonlinear problems, making it suitable for various types of optimization tasks. Whether you're dealing with continuous variables or discrete ones, PSO can adapt accordingly. PSO is used across multiple fields such as engineering for design optimization, economics for resource allocation, and machine learning for training models. Its flexibility makes it a valuable tool in many domains. PSO is also computationally efficient, which is particularly beneficial when dealing with expensive objective function evaluations. Compared to other algorithms, PSO often requires fewer evaluations of the objective function to find a good solution. This efficiency reduces computational time and resource usage. PSO performs well even in high-dimensional search spaces, where other algorithms might struggle. Its ability to efficiently search large, complex spaces makes it a powerful optimization tool. Since each particle operates independently, PSO is naturally suited for parallel processing. This means computations can be distributed across multiple processors, further enhancing computational efficiency. PSO does not rely on gradient information, making it ideal for optimizing functions that are non-differentiable, noisy, or complex. This expands the range of problems where PSO can be effectively applied. PSO is robust and can handle dynamic changes in the optimization landscape. It performs well even when the problem conditions change over time or when there is noise in the objective function evaluations. PSO can be combined with other optimization techniques to create hybrid algorithms. This flexibility allows you to leverage the strengths of multiple methods for enhanced performance. Because PSO is inspired by social behaviors observed in nature, it's intuitive to understand. This makes it easier to explain to stakeholders and team members who may not have a deep technical background. To summarize, PSO offers simplicity in implementation, requires few parameters to tune, is versatile across various problem types, is computationally efficient, robust in different environments, and does not require gradient information. These advantages make PSO a compelling choice for many optimization tasks. While PSO has many advantages, it's also important to understand its limitations and challenges. In the next section, we'll discuss some of the potential drawbacks and how they can be addressed. While particle swarm optimization offers numerous advantages, It's important to recognize its limitations and challenges. Understanding these issues allows us to address them effectively and enhance the algorithm's performance. One significant challenge in PSO is premature convergence. This occurs when the swarm settles too quickly on a solution that isn't the global optimum. When premature convergence happens, the swarm may become trapped in local optima, meaning they settle on a solution that's good but not the best possible one. This issue often arises due to a lack of diversity among particles or when the algorithm focuses too much on exploiting known good areas rather than exploring new ones. Another challenge is that PSO's performance is highly sensitive to its parameter settings. The choice of parameters can greatly influence the effectiveness of the algorithm.